This is Chapter 4, Section 4.9, and we're looking at how we can turn a distributed load into an equivalent point load, and really into an equivalent system that will include a point load as well as a moment, or simply place that point load in the correct location. So let's go ahead and get started. We have a problem here which is 4-142 in edition 14 of the Hibbeler text. It is on page 196 if you'd like to follow along. And it states, replace the distributed load by an equivalent resultant force and specify its location from the beam measured from the pin at A. So we're going to start off as we always do with our given and find. Well, we are basically in this case just given the picture. And we're supposed to find a resultant force. Now we typically use F sub r for that. That's our resultant force. And then they say specify its location on the beam. Now, that can be a little confusing. Basically what they're saying is that we want an equivalent system. We want a system that's going to have the same loading and moment as this existing system that has a distributed load. And in order to do that, they don't want you to give a load and a moment. Instead, to just move that load until it produces the same moment. You always have to ask yourself about which point. In this case, they're telling us the pin at A. So we want to find FR, and we want to find, we'll just call it X, which is going to be the distance from A. Okay, so what we have to do first is we have to figure out how to get the resultant force. Now that is fairly easy because in this case we have a loading equation that makes nice geometric shapes for us. As you can see, I can make two shapes with this. I'm going to make a blue rectangle . Okay, that's a blue rectangle, and then I can make a red triangle. Basically, I'm taking this loading curve and I'm trying to find the area under the curve, because as we know from what we went over in class, the resultant force, we're used to just adding up all of the little forces, all the point loads. But when you have a distributed load, in order to add up all of the area under the curve, it's really equal to the integral across the length of that curve of the loading equation dx. Now we know that this is the same thing as the integral over the area of the area. So in other words, the area under the curve. We know the integral is equal to the area under the curve. In this case we have geometric shapes, a rectangle and a triangle, so we can figure out what that area is fairly simple. So FR is going to be equal to the area of that rectangle plus the area of that triangle. And we're going to have to check our units to make sure that they make sense. So that's going to be the area of the rectangle. The height of the rectangle is going to be 2 kilonewtons per meter. And the base of that, as you can see, is 6 meters because it's the full distance. Okay, take a quick look at our units there. We have meters, canceling meters. We end up with kilonewtons. So it looks like we're doing good. Kilonewtons is a unit of the dimension of force. Then we have to add to it the triangle area. Now that triangle is going to be 2 kilonewtons per meter tall because it starts at 2 kilonewtons and goes to 4. So it's going to be 2 kilonewtons per meter times the base of that triangle, which is going to be 3 meters. But since it's a triangle and not a rectangle, the equation of a triangle area is 1/2 base times height. So we have the height, the base, and 1/2. And you can see our units work out. Meters cancel meters. So that means that our resultant force is going to be equal to 12 kilonewtons plus 3 kilonewtons, 15 kilonewtons. Okay, so we found that resultant force. Now the question really is, where are we going to place that force? Now we know this is 15 kilonewtons. We have to give the direction as well. Well, it's going to be pointed downwards. All of them are pointed down, so that's pretty obvious. I'm going to go ahead and redraw our equivalent system here. So here's my beam. And I'm going to keep my pin support at A and my roller support at B, because it's just asking us about the forces. It's not asking us an equilibrium problem. That's not until chapter 5. And now we know we have a resultant force, 15 kilonewtons. Now we could put that on here, but we don't really know where to place it yet. If I just placed it right in the middle, let's say, if I just placed it right in the middle, that would give us a different moment about point A than the distributed load above. One option is I could place it right on A, which would give us no moment whatsoever, but then I would have to also apply a couple moment that's equal to the moment this distributed load causes. So let's do that first, and then we're going to step to moving the force. So in order to do this, we have to figure out the moment that this distributed load causes. To do that, we're actually going to split up this distributed load into 2 point loads. The first one is going to be the point load because of the rectangle. The point load because of the rectangle is, of course, our 12 kilonewtons. And the point load because of the triangle is 3 kilonewtons. So, my equivalent system here, I'm going to say I have a 12 kilonewton force acting in the centroid of the rectangle. Now, a rectangle centroid is pretty simple. It's right in the middle. So I'm going to put 12 kilonewtons here. And then I have to have the red force, which would be for the triangle, acting in the centroid of that triangle. That would be 3 kilonewton force. Now, the question is, where is the centroid of a triangle? Well, your book is here to help you with that. If you go to the back cover of your textbook, it looks like this. This has different geometrical shapes, and it locates the centroid. The centroid is the dot, and it says C. You can see for the rectangle, the centroid is right in the center, and it's going to be 1/2 the base or 1/2 the height. For a triangle, you can see that the centroid is going to be 1/3 of the height. Now, you're going to have to ask yourself, 1/3 from which side? Hopefully that's obvious to you, because the centroid is the center of mass of an object. So for this particular triangle, we'd want to go 1/3 from the heaviest side, from the side with the most mass. That's going to be the longest side. And that's where the centroid of any triangle is going to be. Let's go back and look at our particular problem. Okay, with our red triangle here, we know that we're 1/3 from one of the sides. What side are we from? Well, obviously, the longer of the two sides is where most of the mass is going to be. So we're going to be 1/3 from that side, which is going to be somewhere around here. I'm going to go ahead and place that over here. I probably should have made that a little shorter because that's only 3 kilonewtons instead of 12. And that blue one should be longer. But you get the idea. The red one is 3 kilonewtons. Okay, now we need some dimensions. Well, we know that this one is 3 meters away, right in the center. And then this one is going to be 1 meter from B, because it's 1/3 of 3, which means it's going to be 2 meters from the other force. And there we go. Now we can figure out what our moment about A is. A resultant moment about A is going to be equal to the moment caused by those 2 point loads representing the distributed loads. You can see that they're both negative. If you put your thumb on A, point your fingers towards the forces, they would tend to bend them back. So we're going to have a 12 negative 12 kilonewtons times the distance from A, which is going to be 3 meters. And then we're going to have negative 3 kilonewtons times 3 meters plus 2 meters, so 5 meters. So the resultant moment about A is going to be equal to negative 36 kilonewton meters minus 15 kilonewton meters. Just negative 51 kilonewton meters. Okay, so we figured out the moment. Now, if we wanted to, we can make a equivalent system. This will be our second equivalent system. Again, we're going to keep the pin supports and the roller support there. Our equivalent system would be, about point A 15 kilonewton force acting right on A so it doesn't create any moment. And then along with that, we're going to need a moment acting in that direction of 51 kilonewton meters. There, that is an equivalent system if we have a fully rigid body to our original distributed load. That would be an appropriate answer, but this problem asks us to go one step further. It says instead of having a point load and a moment, I want you to move that point load so that we just have a single point load that's equivalent to the system. How do we do that? Well, we need to figure out our x bar. Our x bar for this problem is going to give us the same resultant moment about A using the existing force. So we want this moment about A to be our x bar times the resultant force. Now, of course, that's going to be negative because everything we're working with here is negative, and if we want our x bar to be a positive distance, either that or we could plug in our resultant force as negative 15. Either way is perfectly fine. Since I have the resultant force already defined as 15 in the down direction, I'm going to put this negative here to make it work. So now I'm going to have x bar, negative x bar FR is equal to negative 51 kilonewton meters. Solve for x bar. The two negatives cancel, and I get 51 kilonewton meters over the resultant force, which was 15 kilonewtons. 3.4 meters. And what is that telling me? Well, that's telling me if I move the force, the resultant force of 15 kilonewtons, 3.4 meters from A, I'm going to produce the same moment as a distributed load did. So we now have our third equivalent system. The equivalent system has the resultant vector of 15 kilonewtons, and that one is acting .4 meters away from point A. That system is equivalent to the distributed load system for a rigid body, and it's just a single point load away from 3.4 meters away from A. Okay, that solves this problem. Obviously, we would box our answers before we turn them in. And we have one more up here. Let me know if you have any questions, and thank you for watching.